Embracing error-based learning is a fundamental principle for mastering a growth mindset because the brain interprets mistakes as essential signals for adaptation and skill development. Thoughtful. When an error occurs, neurons in relevant cortical and subcortical regions generate error signals that indicate a mismatch between intended and actual outcomes. These signals are not merely notifications of failure, they actively trigger synaptic plasticity, enhancing the brain's ability to adjust strategies, strengthen connections that worked, and weaken inefficient or incorrect pathways. In motor learning, for instance, repeated mistakes during practice refine movement patterns by updating the cerebellum and motor cortex, resulting in smoother, more precise execution over time. Curious, in cognitive and problem-solving tasks, errors highlight gaps in understanding and create opportunities for targeted reflection and adaptation. The emotional interpretation of errors significantly influences whether they lead to growth or stagnation. Individuals with a fixed mindset often perceive mistakes as personal flaws, which activates the amygdala and triggers stress or fear responses. These responses can impair prefrontal cortex function, reducing planning, problem-solving, and adaptive decision-making. In contrast, a growth mindset reframes errors as informative, activating the brain's reward circuits in a way that encourages curiosity, exploration, and iterative learning. Dopamine release in response to understanding and correcting errors reinforces effort-based learning, making repeated practice more engaging and effective. Over time, the association between mistakes and opportunity reshapes neural circuits, making the brain more resilient, adaptive, and efficient in response to future challenges. Error-based learning also interacts with attention and focus. When a mistake occurs, the brain naturally allocates additional attentional resources to the task, increasing awareness of subtle cues, patterns, and contingencies that may have been previously overlooked. This heightened attentional engagement accelerates skill acquisition and supports more accurate memory encoding, particularly when combined with deliberate practice. Importantly, reflection immediately following an error is critical. Consciously analyzing what went wrong, why it happened, and how to adjust promotes deeper learning than passive repetition alone. This reflective process engages the prefrontal cortex and medial temporal lobe, strengthening executive function and declarative memory. The frequency and intensity of errors also modulate learning. Moderate, manageable challenges create a sweet spot where mistakes are frequent enough to drive adaptation, but not so overwhelming that they induce learned helplessness or frustration. Gradually increasing difficulty ensures that the brain continually encounters errors that are within reach of being corrected, maintaining motivation, and maximizing neural plasticity. Cultivating an environment that normalizes mistakes is essential for effective error-based learning. Supportive feedback, mentorship, and peer modeling reinforce the idea that errors are a natural part of growth, reducing stress responses and encouraging repeated engagement with challenging tasks. By consistently reframing errors as opportunities for learning, individuals strengthen the neural pathways that underpin resilience, adaptive behavior, and skill acquisition, transforming setbacks into powerful catalysts for performance enhancement. Seeking and utilizing feedback is a critical component of developing a growth mindset because it provides actionable information that guides learning, skill refinement, and adaptive behavior. The brain constantly compares expected outcomes with actual results, generating prediction error signals when discrepancies occur. Feedback amplifies these signals by supplying external or internal data about performance, which the prefrontal cortex and anterior cingulate cortex use to update strategies, correct errors, and optimize decision-making. When approached from a growth mindset perspective, feedback is not a judgment of ability, but a tool for refining behavior and improving outcomes. This reframing shifts the neural response from a fear-driven amygdala reaction toward a dopamine-mediated reward response that motivates further engagement and learning. The timing and specificity of feedback are crucial for its effectiveness. Immediate feedback allows the brain to link cause and effect more directly, reinforcing correct strategies and correcting mistakes before they are consolidated into ineffective patterns. This is particularly important in skill acquisition, where early repetition of errors can ingrain inefficient motor or cognitive habits. Feedback that is specific, actionable, and focused on behavior or strategy rather than personal traits enhances its utility. For example, rather than stating "you're not good at this," effective feedback emphasizes, "this approach didn't produce the intended outcome." Try this adjustment. This specificity engages executive function circuits, supporting deliberate practice and enhancing neural plasticity. Internal feedback mechanisms are equally important. Self-monitoring, reflection, and metacognition allow individuals to evaluate their own performance, recognize errors, and adjust strategies independently. This process strengthens the prefrontal cortex's capacity for executive control and decision-making, while reinforcing the neural pathways that integrate sensory input, memory, and cognitive planning. When internal feedback is combined with external guidance, learning accelerates because the brain can simultaneously evaluate actions, test alternative approaches, and consolidate adaptive strategies. The emotional interpretation of feedback determines its effectiveness in fostering a growth mindset. Negative feedback often triggers stress responses that activate the amygdala and suppress prefrontal cortex activity, leading to avoidance or defensiveness. Cultivating a growth mindset allows individuals to perceive feedback as non-threatening, emphasizing opportunities for improvement rather than failure. Dopaminergic signaling associated with progress and learning transforms feedback into a motivational driver, reinforcing persistence and resilience. Over time, repeated exposure to constructive feedback reshapes neural circuits to favor exploration, adaptive risk-taking, and engagement with challenges rather than avoidance. Social and environmental factors amplify feedback's impact. Mentors, peers, and supportive learning environments model adaptive responses to feedback, provide guidance, and normalize mistakes as part of the learning process. Observing others engage with feedback productively activates mirror neuron systems, facilitating imitation and reinforcing adaptive neural patterns. Conversely, punitive or judgmental environments can reinforce fixed mindset behaviors, increasing fear of failure and reducing the likelihood of taking on challenging tasks. By consistently seeking, interpreting, and acting on feedback, individuals harness the brain's natural error detection and learning systems, strengthen executive function, and develop resilience. This approach accelerates skill acquisition, enhances performance, and reinforces a growth mindset, making feedback a central tool for long-term improvement and high-level achievement. Engaging in deliberate practice is one of the most effective strategies for mastering a growth mindset because it directly leverages the brain's neuroplasticity to transform effort into skill and performance improvement. Deliberate practice is distinguished from routine repetition by its focus, intentionality, and structured approach to challenging tasks. Unlike passive practice or mere experience, deliberate practice requires setting specific goals, maintaining full attention, receiving continuous feedback, and gradually increasing difficulty to target areas of weakness. This method is effective because the brain learns best when it is actively problem-solving, detecting errors, and updating neural connections in response to new challenges. During deliberate practice, the prefrontal cortex plays a central role in planning, monitoring, and adjusting strategies. By engaging in focused effort, individuals activate executive functions that allow them to identify inefficiencies, formulate alternative approaches, and evaluate progress. The repeated cycles of challenge, feedback, and adaptation strengthen synaptic connections in task-relevant circuits while pruning unused or ineffective pathways. In motor tasks, for example, deliberate practice reshapes the cerebellum and motor cortex, resulting in smoother, more precise movements. In cognitive domains, the process enhances memory encoding, problem-solving efficiency, and reasoning skills. Over time, the brain becomes increasingly capable of executing complex tasks with both accuracy and speed. A critical component of deliberate practice is the appropriate level of challenge. Tasks must be difficult enough to induce errors and engage error-based learning mechanisms, but not so difficult that they produce frustration or disengagement. This sweet spot ensures that the brain remains in a state of heightened attention and arousal conducive to learning, maximizing the efficiency of neuroplastic adaptations. When difficulty is scaled appropriately, dopamine release occurs in response to small successes and progress, reinforcing effort and promoting intrinsic motivation, which is essential for sustaining long-term engagement. Deliberate practice also relies on reflection and conscious adjustment. After each practice session, evaluating what worked, what didn't, and what strategies to modify engages the prefrontal cortex and medial temporal lobe, strengthening executive control and memory consolidation. This reflective component differentiates deliberate practice from mindless repetition, as it ensures that each attempt contributes meaningfully to skill acquisition. By systematically targeting weaknesses and iterating on solutions, individuals create a feedback loop that accelerates learning and reinforces a growth-oriented mindset. Consistency is another key aspect. Frequent, focused practice sessions, even of moderate duration, outperform infrequent, longer sessions in terms of neural adaptation and skill retention. The brain benefits from repeated engagement with challenges, gradually reinforcing circuits involved in attention, motor control, and cognitive processing. Environmental factors, such as minimizing distractions, optimizing learning spaces, and having access to supportive mentors or peers, further enhance the efficacy of deliberate practice by providing additional feedback, modeling, and reinforcement. Through deliberate practice, individuals train their brains to approach challenges systematically, convert effort into measurable improvement, and sustain motivation through intrinsic rewards. This process not only develops specific skills, but also reinforces the neural architecture that underlies resilience, adaptability, and high performance, making it a cornerstone of growth. Mindset mastery. Regulating emotional responses to setbacks is a critical factor in mastering a growth mindset because the way the brain interprets failure directly influences learning, motivation, and long-term performance. When an individual encounters a setback, the amygdala, responsible for processing fear and threat, can trigger stress responses, increasing cortisol and adrenaline levels. These chemicals prepare the body for fight or flight reactions, but simultaneously impair the function of the prefrontal cortex, which governs planning, problem-solving, and adaptive decision-making. When the prefrontal cortex is compromised, individuals are more likely to respond to setbacks with avoidance, frustration, or self-criticism, reducing engagement with challenges and limiting opportunities for growth. By consciously regulating these emotional reactions, the brain can maintain optimal executive function and leverage setbacks as informative signals rather than threats. Cognitive reframing is a powerful technique for emotional regulation in response to failure. This involves intentionally interpreting setbacks as learning opportunities instead of personal deficiencies. Neurobiologically, reframing activates prefrontal regulatory circuits that inhibit overactivation of the amygdala and engage dopaminergic pathways associated with motivation and reward. By connecting effortful behavior to meaningful outcomes and progress, rather than solely to success or failure, the brain releases dopamine in a controlled manner, reinforcing persistence and resilience. Over time, repeated use of cognitive reframing strengthens the neural networks responsible for adaptive coping and reduces the intensity of negative emotional responses to future setbacks. Mindfulness and physiological regulation techniques further support emotional control during challenging experiences. Practices such as deep diaphragmatic breathing, progressive muscle relaxation, or focused attention on present moment sensations activate the parasympathetic nervous system, lowering heart rate and cortisol levels. These physiological shifts allow the prefrontal cortex to function effectively, enabling rational evaluation of the setback and thoughtful planning of corrective strategies. In addition, mindfulness increases awareness of habitual emotional reactions, providing the opportunity to consciously choose adaptive responses rather than reacting impulsively. Social and environmental factors also modulate the ability to regulate emotions after setbacks. Supportive feedback from mentors, peers, or coaches reinforces the perspective that challenges are normal and surmountable, reducing fear-based amygdala activation and promoting engagement with problem solving. Observing role models who persist through failure provides social learning that strengthens mirror neuron circuits, further embedding adaptive emotional responses. Conversely, punitive or overly critical environments amplify stress reactions, making setbacks more likely to trigger avoidance and reinforcing fixed mindset tendencies. The temporal dimension of setbacks is also important. Immediate reflection and adaptive response are more effective than delayed processing because the error signals and associated neuroplastic windows are strongest near the time of the challenge. By responding promptly with regulation, cognitive reframing, and strategic planning, individuals consolidate adaptive neural patterns that facilitate resilience, learning, and performance improvements. By effectively regulating emotional responses to setbacks, the brain maintains executive function, reinforces adaptive neural circuits, and transforms challenges into opportunities for growth. This capacity allows individuals to engage persistently with difficulties, extract maximum learning from mistakes, and sustain motivation, making emotional regulation a foundational skill for cultivating a growth mindset and achieving high-level performance. Cultivating curiosity and intrinsic motivation is a core driver for mastering a growth mindset because it fundamentally shapes how the brain engages with learning, challenge, and skill development. Curiosity activates neural circuits associated with reward, exploration, and attention, particularly in the dopaminergic pathways connecting the ventral tegmental area, striatum, and prefrontal cortex. When the brain perceives a task or topic as intrinsically interesting or valuable, dopamine release increases, enhancing attention, working memory, and learning efficiency. This internal reward system differs from extrinsic motivators like grades, praise, or financial incentives because it sustains engagement even in the absence of external pressure, promoting consistent effort, resilience, and adaptive exploration. Intrinsic motivation allows individuals to persist through difficulty, view challenges as opportunities for growth, and experience deeper satisfaction from skill acquisition, which reinforces a growth-oriented neural architecture over time. Curiosity enhances error-based learning and problem-solving. When individuals approach tasks with a mindset of inquiry, asking how, why, and what if questions, the brain is more likely to detect patterns, generate creative solutions, and integrate new information. This exploratory behavior engages the hippocampus and prefrontal cortex, supporting memory consolidation and flexible thinking. Unlike rigid, goal-oriented approaches, curiosity-driven engagement encourages experimentation and reduces fear of failure because the focus shifts from external judgment to discovery and understanding. The anticipation of acquiring new knowledge or mastering a skill activates the reward system, reinforcing continued engagement even in the presence of challenges or setbacks. Developing intrinsic motivation requires aligning tasks with personal interests, values, or long-term goals. When tasks are perceived as meaningful, the brain assigns greater salience to them, enhancing attentional focus and cognitive resource allocation. This alignment increases persistence during difficult learning periods and strengthens connections in prefrontal and striatal circuits that support sustained effort and self-regulation. Curiosity-driven learning also triggers adaptive stress responses. Moderate levels of challenge paired with personal interest optimize arousal and neuroplasticity without overwhelming the amygdala or triggering avoidance behaviors. Environmental factors play a key role in fostering curiosity and intrinsic motivation. Supportive mentors, collaborative peers, and exploratory learning contexts encourage questioning, experimentation, and independent problem-solving. Environments that reward effort, exploration, and mastery rather than only outcomes reinforce intrinsic motivation by linking effort to meaningful internal rewards. Conversely, highly evaluative or punitive environments can suppress curiosity, shift focus toward fixed outcomes, and promote avoidance behaviors, limiting neural engagement with learning and reinforcing a fixed mindset. Routine practices can also strengthen curiosity and intrinsic motivation. Setting aside time for focused exploration, reflecting on what has been learned, and approaching tasks with an experimental mindset primes the brain to seek novelty and information actively. Encouraging self-directed goals, incremental challenges, and playful experimentation amplifies the reward response associated with learning, embedding growth-oriented habits into neural circuitry. By cultivating curiosity and intrinsic motivation, individuals engage deeply with challenges, optimize neuroplastic adaptation, and maintain persistent effort even when progress is slow or setbacks occur. This internal drive fuels sustained learning, creative problem-solving, and adaptive skill development, creating the neurological and behavioral foundation for mastering a growth mindset and maximizing performance across all domains. Optimizing environment and social influences is a powerful factor in mastering a growth mindset because the brain's learning and adaptation systems are highly sensitive to context, feedback, and social modeling. The neural circuits responsible for motivation, executive function, and emotional regulation are shaped not only by internal cognitive processes, but also by external environmental cues and social interactions. Environments that encourage experimentation, reward effort, and normalize mistakes enhance engagement, resilience, and adaptive learning by reducing fear-based responses from the amygdala while activating dopaminergic circuits linked to exploration, reward, and persistence. Conversely, environments that emphasize judgment, punishment, or comparison can reinforce fixed mindset thinking, increase stress responses, and inhibit the prefrontal cortex's ability to support flexible, growth-oriented strategies. Social influences provide one of the strongest mechanisms for growth mindset development. Observing mentors, coaches, or peers navigate challenges successfully creates social learning opportunities that activate mirror neuron systems, reinforcing adaptive behaviors and strategies. When role models embrace challenges, persist through setbacks, and focus on effort over innate ability, these patterns are mirrored in the observer's neural circuits, strengthening pathways for resilience, motivation, and error-based learning. Similarly, receiving encouragement and constructive feedback in a supportive social context enhances the brain's reward response to learning, amplifying intrinsic motivation and reinforcing engagement with challenging tasks. Peer collaboration and mentoring relationships provide a feedback loop that not only informs skill development, but also helps regulate emotional responses to mistakes, promoting persistence and adaptive problem solving. Physical and cognitive environments also shape growth mindset development. A structured, organized workspace that minimizes distractions enhances attention, working memory, and cognitive flexibility by allowing the prefrontal cortex to allocate resources efficiently. Learning environments that offer clear goals, measurable progress, and incremental challenges optimize engagement and reward anticipation, increasing dopamine signaling and neuroplasticity. Access to tools, resources, and opportunities for exploration further strengthens skill acquisition and reinforces the perception that abilities can be developed with effort and strategy. Conversely, chaotic, punitive, or overly restrictive environments elevate stress responses, increase amygdala activation, and inhibit prefrontal cortex function, making individuals more likely to adopt avoidance behaviors and fixed mindset beliefs. Temporal and routine aspects of environmental optimization are equally important. Consistently exposing oneself to supportive social groups, structured practice settings, and challenging yet achievable tasks primes neural circuits to respond adaptively to difficulty, normalizing persistence, effort, and problem solving. Predictable routines and repetition in these environments strengthen synaptic connections, making growth-oriented responses automatic over time. Encouraging curiosity, collaborative exploration, and reflective practices within these environments further consolidates neural pathways for learning, creativity, and resilience. Optimizing environment and social influences is not limited to external factors. It includes actively shaping one's interactions, surroundings, and exposure to role models that reinforce growth-oriented behaviors. By intentionally curating social and physical contexts that encourage effort, normalize mistakes, and reward adaptive strategies, individuals create conditions that amplify neuroplasticity, motivation, and learning efficiency. This structured alignment of environment, social modeling, and feedback mechanisms accelerates skill development, strengthens resilience, and embeds growth mindset behaviors into daily practice, enabling higher performance and sustained personal and professional growth. When these 6 elements, embracing error-based learning, seeking and utilizing feedback, engaging in deliberate practice, regulating emotional responses to setbacks, cultivating curiosity and intrinsic motivation, and optimizing environment and social influences are applied consistently, they create a synergistic system for enhancing learning, resilience, and high-level performance. Each component reinforces the others, shaping neural circuits that support adaptation, persistence, and creativity. By integrating these strategies into daily life, individuals transform challenges into opportunities, setbacks into learning experiences, and effort into measurable improvement, ultimately unlocking greater potential, sustained achievement, and long-term personal and professional growth.